Have you ever looked up on a clear night and wondered why that faint band keeps appearing in the same place? Why it seems to wait there, familiar and unhurried, as if the sky has chosen one shape it never needs to redraw? Is it a cloud of light, a distant haze, or something closer that only looks far away? And why does it change so much from night to night, barely visible under brighter skies, yet suddenly rich and detailed when the darkness deepens? The Milky Way can feel like the most familiar shape in the night, a pale band that returns again and again, as if the sky has one permanent brushstroke that never quite changes. Some nights, it is only a hint, a thin whitening behind brighter stars. On darker nights, it becomes a river of light, textured and uneven, bright in places, cut through by long, shadowy lanes, as though something vast is present but partially hidden. It is easy to treat that glow as scenery, a background to seasons and weather and ordinary time. Yet the moment the mind lingers on it, the calm begins to widen into a quieter kind of astonishment. That ribbon is not a cloud. It is not a distant wall. It is the interior view of a galaxy, seen from a location that cannot step outside for perspective. So what does it mean to ask how big the Milky Way really is, when every measurement begins from inside the thing being measured, and every glimpse is filtered through dust, distance, and the limits of sight? Is the size the width of the bright disk where most of the stars shine, or is it the faint halo that stretches far beyond the visible band? Is the truest boundary drawn where the last stars thin out, or where gravity still holds on, long after light has faded? And if a galaxy has no crisp edge, only a gradual fading into emptiness, how can any single number feel complete? When a beam of light, the fastest signal nature allows, needs more than 100,000 years to cross the bright span, what does that make of the word across? When the galaxy contains hundreds of billions of stars, and most of its mass is invisible dark matter, what does big even mean? Brightness, mass, reach, or influence? The Milky Way is often described as a spiral, a rotating disk with arms curving outward from a crowded center. Yet that shape is never seen directly from Earth. It is reconstructed, patiently, from maps of gas, from the positions of star-forming regions, from the measured motions of stars, and from comparisons with other galaxies that show their spirals openly. The picture is indirect, but it is not guesswork. It is a mosaic built from many kinds of evidence, each one adding depth to a structure that can only be understood by inference. In that sense, the true scale of the Milky Way is not a single distance, but a set of scales nested inside one another. There is the scale of the night sky as it appears to human eyes. There is the scale of the stellar disk where most starlight is concentrated. There is the scale of the halo of ancient stars and globular clusters that surround the disk like a faint atmosphere. And beyond even that, there is the scale of the dark matter halo, a silent mass whose presence is known by gravity alone, extending far past what any photograph could capture. To move through these layers is to move through different meanings of size. Not merely how wide the galaxy is, but how far it reaches, how much it contains, and how long it takes for information to travel from one region to another. The Milky Way is measured not only in distance, but in time, because the unit that makes the most sense at these scales is the light year, a way of turning travel into a clock. And so the journey toward the galaxy's true scale begins with a simple shift of units, away from the lengths that belong to roads and continents, and toward distances so large that time itself becomes part of the measurement. Before the disk and the halo, before the center hidden behind dust, before the question of edges. It helps to start with the ruler astronomers use when ordinary numbers stop being useful, and to see what it means when distance is spoken in years of light. A light year is often misunderstood as a measure of time, but it is a distance, defined by how far light travels in 1 year as it moves through empty space. Light itself travels at nearly 300,000 kilometers every second. In that single second, it could circle the Earth more than 7 times. When that speed is carried forward through minutes, hours, days, and finally an entire year, the result is a distance of almost 10 trillion kilometers. That is 1 light year. Even that single unit already stretches intuition. 10 trillion kilometers is not a distance the human mind evolved to picture. And yet, within the Milky Way, 1 light year is considered small. The nearest star system to the Sun lies more than 4 light years away. That means the light reaching Earth from that neighboring star began its journey more than 4 years ago, long before it ever reached the retina of a human eye. When astronomers speak of the Milky Way, they speak in tens of thousands of these units. The bright disk of the galaxy, the region where most of the stars are found, spans roughly 100,000 light-years from one side to the other. A beam of light leaving one edge of that disk would require more than 100,000 years to arrive at the opposite side, even traveling at the fastest speed the universe allows. That figure alone begins to hint at scale, but it does not yet describe where we are within it. The Sun does not sit at the center of the galaxy, nor near its outer rim. It occupies a position partway out, roughly 26,000 light-years from the galactic center. The light arriving from that central region tonight began its journey when early humans were still leaving marks on cave walls, long before agriculture, cities, or written language. Every direction we look within the Milky Way is therefore a view into the past. The stars scattered across the sky are not seen as they are now, but as they were when their light departed, sometimes thousands, sometimes tens of thousands of years ago. The farther the distance, the deeper the look into history. Space becomes a layered archive where distance and time are inseparable. This is one reason the size of the galaxy is not only a matter of length, but of duration. To cross the Milky Way is not just to cross space, but to cross epochs. Even the slow orbit of the Sun reflects this. Moving at nearly 800,000 kilometers per hour, the Sun still requires about 225 million years to complete a single circuit around the galactic center. In the entire lifetime of the Sun so far, it has completed only about 20 such orbits. From this perspective, the Milky Way is not a static object. It is a structure in motion, unfolding on timescales that dwarf human history. Stars are born, evolve, and die while slowly circling the center. Spiral arms persist as patterns, even as individual stars drift through them. The galaxy turns, but so slowly that its motion is invisible within any single lifetime. Yet for all this movement, the Milky Way presents itself to human eyes as a steady band of light. The reason lies in its shape. The galaxy is not spherical. It is flattened into a disk, with most of its stars confined to a relatively thin plane. From within that plane, looking outward along its length, stars overlap in dense layers. Their combined light blends together, forming the pale streak that stretches across the night sky. This band appears brighter in some directions than others. When looking toward the constellation Sagittarius, the line of sight passes toward the galactic center, through a thicker concentration of stars. When looking in the opposite direction, toward the outer disk, the star density thins and the band fades. These variations are not clouds or gaps, but changes in how much of the galaxy lies along the line of sight. Dark lanes interrupt the glow, caused by vast clouds of dust drifting between stars. These clouds block visible light, carving shadows into the Milky Way's brightness. They do not mark empty regions, but places where stars are hidden behind veils of interstellar material. The galaxy is full of them, it appears, its light selectively filtered before it ever reaches Earth. Understanding this flattened structure is essential for grasping the galaxy's size. The Milky Way is wide, but it is also thin by comparison. The disk measures roughly 100,000 light-years across, but only a few thousand light-years thick. From above or below, it would appear as a narrow sheet of stars with a swollen center. From within, it becomes a glowing horizon. At the heart of that horizon lies the central bulge, a dense, rounded concentration of stars, packed far more tightly than those in the disk around us. It is here that the galaxy's gravity deepens, where stellar orbits shorten and speeds increase, and where the true anchor of the Milky Way resides. But the center is not revealed easily. Dust obscures it, scattering visible light and leaving its most dramatic features hidden from ordinary sight. To understand the true scale of the Milky Way, it is not enough to trace the disk alone. The galaxy extends beyond the bright band, beyond what human eyes can see, into regions where stars grow sparse and light gives way to darkness. It is in those outer layers that the question of size becomes more complex, and where the Milky Way begins to exceed its familiar outline. Beyond the bright disk that defines the Milky Way to our eyes lies a much quieter and less obvious structure. This region is called the halo, and it surrounds the galaxy like a faint extended atmosphere. Unlike the disk, the halo does not glow as a continuous band. Its stars are sparse, widely separated, and often ancient, relics from the earliest chapters of the galaxy's history. The halo contains globular clusters, dense spherical gatherings of hundreds of thousands of stars bound tightly together. These clusters orbit far above and below the galactic plane, some tens of thousands of light-years from the center. Many of them are more than 10 billion years old, meaning they formed when the Milky Way itself was still assembling. Their existence tells us that the galaxy did not form all at once, but grew through stages, drawing in material over immense spans of time. Individual stars also wander the halo, following tilted and elongated paths rather than the neat circular orbits of the disk. Some of these stars likely formed in the Milky Way's earliest era. Others were born in smaller galaxies that later merged with ours, their original homes pulled apart by gravity. Today, their stars remain as scattered traces, moving silently through the halo, no longer belonging to any distinct system. The halo already stretches the idea of size, well beyond the familiar figure of 100,000 light-years. Including these outer stars and clusters, the Milky Way extends closer to 300,000 light-years from one side to the other. Even here, however, the edge is not sharp. The density of stars thins gradually. There is no boundary you could cross and declare that the galaxy has ended. It simply fades. Yet even this expanded view does not capture the full reach of the Milky Way. The most massive component of the galaxy is something that cannot be seen at all. Surrounding both the disk and the stellar halo is a vast dark matter halo, an invisible structure whose presence is revealed only through gravity. Stars in the outer regions of the galaxy move faster than they should if only visible matter were present. The orbits of satellite galaxies curve in ways that demand additional mass. Light from distant objects then subtly as it passes through the galaxy's gravitational field. All of this points to a hidden component outweighing the stars themselves. This dark matter halo is immense. Models and observations suggest that it may extend close to 1 million light-years from the galactic center, far beyond the last visible stars. If this is included, the Milky Way is not merely a spiral disk with a faint halo, but a colossal sphere of influence whose true size is defined by gravity rather than light. In this sense, the familiar galaxy is only the luminous core of something far larger. The difficulty, then, is deciding what it means to measure the size of a galaxy. If size is defined by where stars shine, the answer is 100,000 light-years. If it includes the halo of ancient stars, the figure triples. If it includes the full reach of dark matter, the number grows by an order of magnitude. Each definition is correct within its own context, yet none tells the entire story. This ambiguity is not unique to the Milky Way. Other galaxies show the same pattern. Their bright disks are only part of their total mass and reach. Around them lie extended halos of stars and dark matter, overlapping with those of neighboring galaxies. In fact, the dark matter halos of the Milky Way and the Andromeda galaxy already intersect, even though their luminous disks remain millions of light-years apart. Long before their stars meet, their gravitational domains have begun to merge. This overlap places the Milky Way within a larger structure known as the local group, a small collection of galaxies bound together by gravity. Andromeda is the largest member, slightly more massive than our own galaxy. The Milky Way and Andromeda dominate this group, surrounded by dozens of smaller dwarf galaxies. These companions orbit within the extended halos, their motions shaped by the invisible mass that surrounds both giants. The presence of these satellites offers further clues to the Milky Way's scale. Dwarf galaxies such as the Large and Small Magellanic Clouds orbit within our halo, trailing streams of gas and stars as they move. Some, like the Sagittarius dwarf galaxy, are already being torn apart, their stars stretched into long arcs that wrap around the Milky Way. These stellar streams extend tens of thousands of light-years, marking the paths of galaxies that are in the process of being absorbed. Each of these interactions adds to the galaxy's mass and reshapes its outer regions. The Milky Way grows not only by forming new stars, but by incorporating entire smaller galaxies into its halo. Over billions of years, this gradual process builds the extended structure we observe today. The size of the galaxy is therefore not fixed. It is the result of a long history of accumulation and change. Despite this vast reach, the Milky Way remains modest by cosmic standards. Some galaxies are several times larger, with disks spanning hundreds of thousands of light-years and halos extending even farther. Others are much smaller, compact systems with only a few billion stars. Our galaxy sits comfortably in the middle, neither extreme nor exceptional, a typical large spiral shaped by the same physical laws as countless others across the universe. To place ourselves within this scale, it helps to return to our own position. The Sun lies within the Orion Arm, a minor spur between two major spiral arms. This region is quieter than the crowded center and richer than the sparse outskirts. It is far enough from the core to avoid intense radiation and gravitational chaos, yet close enough to benefit from generations of star formation that enrich the galaxy with heavier elements. From this location, the Milky Way fills the sky, but only as a partial view. We see the disk edge on, its light compressed into a band. We cannot see the halo directly, and we cannot see the dark matter at all. And yet, we are embedded within all of it, moving along with the stars and gas, carried by the same gravitational field that binds the entire structure together. When the size of the Milky Way is considered in this way, it becomes clear that no single number can fully capture it. The galaxy is not a circle drawn on a page, but a layered system whose extent depends on what is being measured. Light defines one boundary. Stars define another. Gravity defines the largest of all. The Milky Way is therefore not just wide, but deep. It extends not only across space, but across time, containing stars from its earliest days and structures still forming today. Its true size is written in orbits that take hundreds of millions of years to complete, in halos that stretch far into darkness, and in gravitational reach that connects it to its neighbors long before their light meets. To understand how this immense structure compares to others, astronomers often look outward, using the Milky Way as a reference point rather than an isolated case. When viewed alongside nearby galaxies, its scale becomes clearer. The Andromeda galaxy, our nearest large neighbor, spans roughly 200,000 light-years across its visible disk, making it somewhat larger than the Milky Way. Its halo likely extends even farther, similar in proportion to our own. Other spirals across the universe show a wide range of sizes, some smaller and tighter, others sprawling and diffuse, but the Milky Way sits comfortably among the large spirals rather than at either extreme. This comparison reveals something important. The Milky Way feels vast because we live inside it, but in the broader universe, it is not unusual. Galaxies of similar size and structure are common. Hundreds of billions of stars arranged in spiral arms, embedded within massive dark matter halos, appear again and again across the cosmos. Our galaxy is one example of a widespread pattern rather than a rare exception. That pattern is not static. Galaxies evolve. Over time, their sizes change as they interact with their surroundings. The Milky Way has grown through countless mergers with smaller systems, and it will continue to do so. Evidence of this growth is written across the halo in the form of stellar streams, think ribbons of stars that trace the paths of long-consumed companions. Each stream marks an increase in the galaxy's reach, a reminder that its present size is the result of a long history rather than a fixed starting point. The future will bring further change. The Milky Way is moving through space along with the rest of the local group, and its path is slowly converging with Andromeda's. In roughly 4 to 5 billion years, the two galaxies will begin a prolonged interaction. Their dark matter halos already overlap, and their mutual gravity is drawing them together. When their visible disks eventually meet, the encounter will reshape both galaxies, stretching their arms, redistributing their stars, and likely forming a single larger system. This future merger highlights another way to think about size. A galaxy is not only defined by its current dimensions, but by the region of space it will eventually occupy. The Milky Way's gravitational influence extends far beyond its luminous boundaries, and that influence is already affecting its neighbors. In this sense, the galaxy's size includes not only what it contains now, but what it is in the process of becoming. From within the disk, however, these grand scales are difficult to perceive. The stars near the Sun are separated by several light-years, giving the impression of a relatively empty environment. The galaxy's immense density only becomes apparent when looking along the plane of the disk, where countless stars overlap in the line of sight. Even then, the vast majority remain unseen, too distant or too faint to register against the background. Our own motion through the Milky Way adds another layer to this perspective. The Sun follows a nearly circular orbit around the galactic center, traveling at hundreds of kilometers per second. This motion is smooth and steady, guided by the combined gravity of stars, gas, and dark matter. Over millions of years, the Sun drifts slightly inward and outward, passing through different regions of the disk. The galaxy is not a rigid structure, but a flowing system in which stars migrate over time. These slow movements mean that the Milky Way we describe today is not exactly the same Milky Way that existed in the distant past. Its size has increased as new material has been added. Its shape has been subtly altered by interactions. Its stellar population has changed as generations of stars have formed and died. The numbers used to describe it, 100,000 light-years, 300,000, a million, are snapshots taken at one moment in an ongoing process. Even so, these measurements remain meaningful. They give us a framework for understanding where we are. They allow us to place the solar system within a structure far larger than itself, and to see that structure as part of an even larger cosmic environment. Without such measurements, the Milky Way would remain only a vague glow in the sky. With them, it becomes a defined, though still awe-inspiring, object of study. When astronomers map the galaxy, they rely on a combination of techniques. Nearby stars are measured using parallax, the tiny shift in position caused by Earth's orbit around the Sun. More distant stars are measured using their intrinsic brightness, or by tracing the distribution of gas and dust. Motions within the galaxy reveal the influence of unseen mass. Together, these methods build a three-dimensional picture from within, assembling a model of size and shape piece by piece. Despite all this effort, uncertainty remains. The outermost extent of the dark matter halo, in particular, is difficult to define. Its density decreases gradually rather than ending abruptly, blending into the surrounding cosmic web. At some point, the Milky Way's influence gives way to that of other galaxies and the collective pull of the local group. Where exactly that transition occurs is still a subject of research. The edge of the galaxy, in this deepest sense, is not a line but a region. This idea challenges everyday notions of boundaries. On Earth, edges are often clear. Coastlines, walls, borders define where one thing ends and another begins. In the universe, especially at the scale of galaxies, boundaries are soft. Structures overlap. Influences fade rather than stop. The Milky Way exemplifies this. Its stars thin into the halo. Its halo merges with neighboring halos. Its gravity stretches far beyond its light. From a human perspective, it can be helpful to bring this vastness back to a more familiar scale. If the Milky Way were reduced to the size of a large city, the solar system would be smaller than a single grain of sand. Even then, most of the city's mass would be invisible, shaping the movement of everything within it. Such comparisons cannot fully capture reality, but they hint at how deeply embedded we are in a structure far larger than any everyday experience. Ultimately, asking how big the Milky Way really is leads to an answer that depends on context. It is 100,000 light-years wide in visible starlight. It is several 100,000 light-years across when its halo of ancient stars is included. It is close to 1,000,000 light-years in gravitational reach when dark matter is taken into account. Each figure describes a different aspect of the same galaxy. What remains constant across all these definitions is the sense of scale they convey. The Milky Way is not a backdrop. It is an environment, a system that contains us completely. Every atom in the solar system is bound to it. Every orbit, from planets to stars, unfolds within its gravitational field. Its size is not something we observe from afar, but something we inhabit, moment by moment, as it turns slowly through space. From that perspective, the Milky Way is not simply a structure we look at, but a system we move within. Every moment, the solar system is carried along by the galaxy's rotation, tracing a path shaped by forces that act on scales far beyond anything directly perceptible. The sense of stillness we experience is an illusion created by immense distances and slow change. In reality, the galaxy is alive with motion. The Sun's orbit around the galactic center takes roughly 225 million years to complete. This span is sometimes called a galactic year. In the entire history of complex life on Earth, the Sun has completed only a handful of these orbits. Dinosaurs rose and vanished in less than one galactic circuit. Human history occupies only a small fraction of one. Against this backdrop, the Milky Way's size is inseparable from its timescale. To be large in space is also to be large in time. As the Sun moves along its path, it does not follow a perfectly fixed route. It oscillates slightly above and below the galactic plane, passing through regions of differing star density. Over long periods, it also drifts inward and outward by small amounts. These migrations are gentle, but they remind us that the galaxy is not rigid. Stars respond to gravitational influences from spiral arms, passing clouds, and long-range tidal forces. The Milky Way is a fluid structure, not a frozen one. Spiral arms themselves are not solid objects that stars remain trapped within. They are patterns, waves of higher density that move through the disk. As gas enters these regions, it compresses and forms new stars, lighting up the arms. Older stars gradually drift away, even as the spiral pattern persists. This means that the apparent shape of the galaxy is maintained over long periods, even though its individual components are constantly changing. This distinction matters when thinking about size. The Milky Way's spiral arms define much of its visible extent, but they are not permanent features in the way a solid framework would be. The arms trace where star formation has been active, not the full distribution of mass. Beyond them, stars continue to orbit in the disk and halo, contributing to the galaxy's reach even if they do not define its brightest outlines. The central region of the galaxy plays a critical role in shaping this motion. At its core lies Sagittarius A, the supermassive black hole with a mass of about 4 million suns. Although it occupies a region smaller than the solar system, its gravitational influence extends far outward. It acts as an anchor, contributing to the stability of stellar orbits in the inner galaxy. Yet, despite its dramatic nature, it does not dominate the galaxy's mass. The combined mass of stars and dark matter far outweighs that of the central black hole. This balance underscores an important point. The size of the Milky Way is not controlled by a single object or region. It emerges from the collective gravity of countless components, stars, gas, dust, and dark matter, distributed across vast distances. No single boundary defines it. Instead, its structure is the result of equilibrium, a balance between motion and attraction maintained over billions of years. When astronomers attempt to visualize the Milky Way as a whole, they often turn to observations of other spiral galaxies. These external views provide context. From afar, galaxies similar to ours appear as luminous disks with graceful arms, surrounded by faint halos. Their sizes vary, but the underlying pattern repeats. This repetition suggests that the Milky Way's scale is not arbitrary. It reflects the typical outcome of galaxy formation under the laws of gravity and cosmic expansion. Those laws began shaping galaxies shortly after the universe itself formed. In the early universe, matter was distributed more evenly. Over time, slight variations in density grew under gravity, drawing material together. Dark matter played a central role, forming massive halos that attracted gas. Within those halos, stars ignited and galaxies took shape. The Milky Way's size today reflects the mass of its dark matter halo and the amount of material it was able to gather over cosmic history. Because of this, size is linked to environment. The Milky Way did not form in isolation. It grew within a region populated by other galaxies and streams of matter. Its interactions, mergers, and accretions all contributed to its present dimensions. Had it formed in a sparser region, it might be smaller. Had it formed in a denser cluster, it might be larger or more distorted. Its current scale is the outcome of a particular cosmic neighborhood. The local group itself is part of an even larger structure, sometimes called the Virgo supercluster. On these scales, individual galaxies become points within vast networks of filaments and voids. The Milky Way's size, impressive on its own, becomes one element within a much larger hierarchy. This nesting of structures, planets within solar systems within galaxies, galaxies within groups and clusters, is a defining feature of the universe. And yet, for all this nesting, the Milky Way remains the largest structure we can meaningfully call home. Beyond it, distances become so great that other galaxies are effectively unreachable with any foreseeable technology. Their stars will never mix with ours except through the slow choreography of gravitational interaction. In that sense, the Milky Way's size defines the boundary of our practical universe, the region where matter, energy, and history are directly connected to us. This connection is physical as well as conceptual. The elements that make up the Earth and its life were forged in earlier generations of stars within the Milky Way. Supernova enriched the galaxy with heavier elements, which later condensed into new stars and planets. The solar system formed from material already shaped by the galaxy's past. To ask how big the Milky Way is, then, is also to ask how extensive the reservoir of matter is, from which worlds like ours can arise. When viewed this way, the galaxy's size takes on a quieter significance. It is not merely a statistic, but a measure of capacity. A larger galaxy can host more stars, more planetary systems, more opportunities for complexity to emerge. The Milky Way's hundreds of billions of stars imply an enormous number of potential worlds, scattered across its disk and halo. Each one occupies its own small neighborhood within the same vast structure. Yet despite this abundance, the galaxy remains mostly empty. The average distance between stars in the disk is several light-years. In the halo, it is much greater. Space within the Milky Way is dominated by emptiness, with islands of matter separated by immense gaps. This emptiness is part of what allows the galaxy to be so large without becoming chaotic. It gives stars room to orbit without constant disruption. This balance between scale and sparseness is one of the Milky Way's defining features. It is enormous, yet stable, vast, yet orderly. Its size does not lead to collapse or confusion, but to long-term coherence. Over billions of years, it has maintained its structure even as individual components change. That endurance is as much a part of its scale as any measurement in light years. As the Milky Way continues its slow evolution, its size will change. New stars will form. Others will die. Dwarf galaxies will be absorbed. The merger with Andromeda will reshape it entirely. The numbers used to describe it today will become historical, replaced by new ones appropriate to a future galaxy. Size, in this sense, is not fixed. It is a chapter in an ongoing story. From our place within it, however, the galaxy's immensity remains constant. The distances between stars, the time it takes light to cross the disk, the slow orbit of the Sun, all define an environment that changes far more slowly than human lives. The Milky Way provides a stable backdrop against which generations rise and fall. Its size ensures that change, while inevitable, unfolds gently. And so, when the question is asked, how big is the Milky Way really? The most accurate answer may be that it is as large as gravity allows it to be, as extended as its history has made it, and as vast as the invisible matter that binds it together. It is a galaxy defined not by a single edge, but by a continuum. Light fading into darkness, stars giving way to empty space, influence stretching beyond sight. We live inside that continuum, carried along by its motion, bound by its gravity, shaped by its past. The Milky Way is not something that begins or ends at a clear boundary. It is something that surrounds us, encloses us, and extends far beyond what we can ever see directly. Its size is not just a number. It is a condition of existence, the scale on which our corner of the universe unfolds. When all of these layers are held together, the Milky Way begins to feel less like an object with dimensions and more like an environment with depth. Its size is not something that can be traced with a single line or captured by a single figure. It is revealed through overlapping measures: light, mass, motion, and time, each one describing a different aspect of the same structure. The bright band seen from Earth represents only the most immediate layer, the region where stars are concentrated and their light overlaps in our line of sight. Beyond that lies the quieter halo, populated by ancient stars and clusters whose orbits carry them far above and below the disk. Beyond even that lies the dark matter halo, an invisible framework extending far into intergalactic space, binding the entire system together. None of these layers replaces the others. They coexist, nested within one another, forming a galaxy whose true size depends on how deeply one chooses to look. From this perspective, the familiar figure of 100,000 light-years is not wrong, but it is incomplete. It describes the region where starlight dominates, not the full reach of the galaxy. The larger figures, hundreds of thousands or close to 1 million light-years, describe the extent of gravity, not the extent of light. Each answer is correct within its own frame, and the full truth lies in holding them together rather than choosing between them. This layered view also changes how the Milky Way is experienced from within. We do not sense its size directly. We feel no tug from its outer halo and no awareness of its full span. Instead, we experience a quiet local sky, a handful of nearby stars, the slow passage of seasons, and the steady motion of the Sun. The galaxy's immensity operates in the background, shaping everything without demanding attention. Even the most dramatic features of the Milky Way remain distant. The crowded center lies far away behind thick curtains of dust. The ancient halo stars move on timescales far longer than a human life. The dark matter halo announces itself only through careful measurement. The galaxy's size is therefore not something that overwhelms the senses. It is something that emerges through understanding. This may be one reason the Milky Way has inspired both science and reflection across cultures and centuries. To early observers, it was a path, a river, a bridge across the sky. To modern astronomy, it is a rotating spiral embedded in a vast halo of unseen mass. These views differ in explanation, but they share a recognition that the band of light overhead points to something far larger than itself. From a wider cosmic viewpoint, the Milky Way's size also finds its place among others. It is large enough to host hundreds of billions of stars, yet not so large as to be rare. It is extended enough to influence its neighbors, yet still shaped by them in return. It is massive enough to endure for billions of years, yet not immune to change. Its scale places it firmly within the common patterns of the universe, a typical spiral galaxy in an extraordinary cosmos. This balance between the ordinary and the immense is part of what makes the Milky Way a useful lens through which to understand the universe. By studying its size and structure, astronomers learn how galaxies form, grow, and interact. By placing our location within it, we gain perspective on where we are, not just in space, but in time. The galaxy's size becomes a measure of history as much as of distance. As the Milky Way continues its slow evolution, its boundaries will continue to shift. Stars will migrate. Halos will overlap more deeply. The eventual merger with Andromeda will create a new galaxy whose size and shape will differ from what we know today. The Milky Way, as it exists now, is one moment in a much longer sequence. Its current dimensions are a snapshot taken partway through an ongoing process. And yet, within that process, the galaxy offers a remarkable sense of continuity. For billions of years, it has maintained a coherent structure. For billions more, it will continue to do so, even as its details change. Its size ensures that transformation unfolds slowly, allowing long periods of relative stability. That stability is part of what has allowed planetary systems and, on at least one world, life to develop and persist. In the end, asking how big the Milky Way really is leads to a deeper understanding of scale itself. Size at this level is not a single measurement, but a relationship between light, gravity, and time. The galaxy is as large as its stars can orbit, as far-reaching as its gravity can bind, and as old as the history written into its halo. This is not a size that can be pictured all at once. It must be approached gradually, layer by layer, until the mind adjusts to distances measured in tens and hundreds of thousands of light-years. What begins as a pale band in the sky becomes a vast system enclosing everything familiar, a structure so large, but it turns distance into history and motion into patience. When that adjustment settles in, the Milky Way no longer feels like something distant or abstract. It becomes the setting within which every ordinary moment takes place. The ground beneath your feet, the air around you, the quiet movement of the night, all exist inside a structure whose scale far exceeds anything the senses can register. The galaxy does not announce itself with force. It simply contains. The stars overhead, scattered and calm, are the nearest points of a system that stretches far beyond sight. Their light has crossed years, sometimes thousands of years, to arrive. Behind them lie countless others, hidden by distance or dust, and beyond those lie regions where light itself thins away, but gravity remains. The Milky Way holds all of this together without urgency, turning slowly, steadily, on timescales that make human history feel momentary. From this vantage, the question of size shifts once more. It is no longer only about how far the galaxy reaches, but about what it sustains. It sustains long-lived stars that shine for billions of years. It sustains wide, stable orbits that allow planets to persist. It sustains a balance between order and change that has lasted longer than any civilization and will last long after those alive today are gone. Its size is the reason this continuity is possible. The galaxy is not crowded in the way cities are crowded. It is vast precisely because most of it is empty. Stars are separated by light years of space. Even in the dense inner regions, collisions are rare. This openness allows the Milky Way to be both immense and stable, extended without being chaotic. Its scale is not excess. It is spacing. When seen this way, the Milky Way becomes less intimidating and more quietly reassuring. It is large enough to absorb change without disruption. Mergers unfold over billions of years. Orbits shift slowly. Patterns endure even as individual stars move on. The galaxy's size smooths time, stretching events so that nothing happens suddenly on the scale of a human life. And within that smoothing, there is room for perspective. The Milky Way does not require constant attention to exist. It turns whether it is observed or not. It surrounds whether it is measured or not. Its vastness does not press inward. It simply remains. The stars do not rush. The arms do not tighten. The halo does not collapse. The galaxy persists. So when the night sky appears calm and unchanged, that calm is real. It reflects a structure whose size is so great that its motion becomes gentle. The Milky Way's true scale is revealed not through drama, but through patience. Through distances so large they take tens of thousands of years to cross. Through orbits that take hundreds of millions of years to complete. Through a gravitational reach that fades gradually rather than ending sharply. In that sense, the galaxy's size is not something to be grasped all at once. It is something to rest within. A quiet fact of existence. A reminder that the world you experience each day unfolds inside a system far larger and older than any immediate concern, yet steady enough to hold those concerns without disturbance. The Milky Way will continue to turn long after tonight has passed. Its stars will continue their paths. Its halo will continue to extend into darkness. Its gravity will continue to bind what belongs together. And wherever you are within it, whether under a clear sky or beneath clouds, that vast structure remains unchanged in its presence. It does not demand understanding to exist. It simply does.